Hello, my name is Piotr, and today I have come here to assist Ivan in improving the test stand. My main task will be to return the energy that was previously wasted or lost back into the motor that is currently being tested. This will help make the testing process more efficient and sustainable. I can say right away that this is not a perpetual motion machine. Our system will consist of simple components, namely a diode rectifier, and 3 DC-DC converters modified from Toyota Aqua units, which are located here, right here with me. The power we get on this shaft can be transferred to the electric generator. The electric generator produces what is known as alternating current, which then goes to the rectifier unit where it is converted to direct current, but the voltage there is much lower than on the motor under test, right? And we just need to raise it to the required level. We will raise it accordingly using the DC-DC converters, which are specifically designed for this purpose. But not just raise it, we can even adjust the current, the amount of electrical flow that will help it spin more efficiently for this motor right here. Right now we have a small remote control. In the future, most likely, we will create a sophisticated control system for this test bench, which will allow us to electronically control the load. That is, we can create a load of 20 newtons or 30 newtons and so on. The main goal of our modification is to eliminate these resistive blocks that previously created a load on this shaft. And the energy that used to be lost as heat, we will now convert back into electricity and use it to power the test motor, thereby improving the overall efficiency of the system. Now I'll step away from here. This bridge right here still needs to... Yeah. You don't want to do something? So we've managed to wire up the test stand. We've now started 3 DC-DC converters and can now test our motor. The installation of the blocks is complete. The system is now energized. The mains voltage is 295 volts. It is rectified from the isolation transformer. The controller is now powered. Now we're going to spin up this electric motor, and this generator right here will create a braking torque, which we can adjust as needed. Wait, go ahead and start when you're ready. And we'll now see the current that is actually generated by this system. Now we'll simply measure the voltage supplying our controller. And it's 291 volts. The voltage is currently coming from the transformer, where it is rectified by a diode bridge, and that is essentially how we obtain this value. Now we are carefully applying the maximum load to the shaft and starting up our test motor. The load can be released slowly and carefully, and then gradually reduced. The motor is now spinning at 3000 RPM. The load on the shaft in this particular case is 24 Newton meters. The shaft power, as measured, is a total of 8 kilowatts. Now we'll measure the current in our system, which is regenerating all of this. The current is about 25 amperes. That's what the system has returned. And what's the total consumption? 38 amps. So if we subtract 25 from 38, we get the current that we're drawing from the grid in this setup. There are currently no resistors, and the heat is dissipated through this radiator using a water cooling system. We started up the system, and it showed good results. We managed to create a load on the shaft and control this load with it. This demonstrates the effectiveness of the system in handling the load and maintaining stable operation.
I'd also like to briefly point out that since we now have the ability to electronically adjust both the load and the engine power, we now have the opportunity to bring this to full automation. Since we have outputs from the torque sensor, a power output, load control, and engine control, it is actually even possible to write some software up to the point of testing the engine with the press of a single button. In other words, a program that will run the engine through all different modes, measure its efficiency, power, and actually generate graphs and results.
Unfortunately, a perpetual motion machine, as we might have hoped, simply did not work out for us. As you saw for yourself, when the system is operating at a load of 8 kilowatts, it outputs a current of about 25 amperes at 290 volts, while the controller consumes 32 amperes at 290 volts. But I think you can just do a simple calculation here and see that the efficiency that's lost as thermal energy and the mechanical conversion. It's being drawn from the outlet.
And that's all for today. Subscribe to the channel, stay tuned for more, and goodbye everyone.
Friends, well, and detailed information on how to convert a Toyota Aqua inverter into such a step-up DC-DC converter will be available on the Engineer's Time channel. The link is in the description.